what is the yield of sodium acetate crystals. So this is a trihydrate form of sodium acetate obtainable from a vacuum crystallizer operating at 1.33 kilonewton meter squared. So this is your kilopascal pressure when it is supplied with 0.56 kilograms per second of a 40% aqueous solution of the salt at 353 Kelvin. Now, the boiling point elevation of the solution is 11.5 degree Kelvin. And you are provided with the following data. Some goes with the problem, the others I added. That way, everything we need not anymore go to the property tables if there's a need for us to go and find such information. So very important, the heat of crystallization. The problem has to give this if we are to determine the amount of water evaporated and it's not given in the problem how much is this amount of water evaporated from the original feed. So in this case, our heat of crystallization is 144 kilojoule per kilogram of the trihydrate. Now the heat capacity is given. So this is referring to the heat capacity of the feed to be 3.5 kilojoules per kilogram degree Kelvin. And then the latent heat of water. So this latent heat of water, which is taken at a pressure of 1.33 kilopascal, is supposed to be taken from the steam table. So should the problem not anymore mention this specifically, you are the one who's going to get this from the steam tables. And what is this? This latent heat is just the difference of the saturated vapor enthalpy and the saturated liquid enthalpy. As to the boiling point of water, since there is a mention here of the boiling point elevation, you are also going to base it on the pressure, the crystallizer operating pressure, which is 1.33. Now, remember that this is the boiling point of pure water. It does not yet contain your solids. And that is why the problem ended with the statement that due to the presence of the solids, though it's not specifically mentioned, the boiling point of the solution increased by 11.5 degrees Kelvin. So no term about an increase in the boiling point, but that by the fact that it's mentioned here, it's the boiling point elevation, meaning based on the saturation boiling point of water based on the operating pressure of the crystallizer, you are to add this one up so that you will have the true boiling point of your water, sodium acetate trihydrate crystals. So it's already a magma, a solution of your liquor and your crystals. So you are to get this also from the steam table. So should this be not specifically given, then get it from the steam tables. I'm referring to the boiling point of your solution of your water, then add up the boiling point elevation due to the presence of the solids. Then we're given the very important solubility of sodium acetate. When you read Colson, whenever he mentions about solubility of any salt, in particular with water, automatically he has it labeled already as C sub 2, or that is the final concentration of your crystal and solvent solution. Now, in the case in the board exam, if it's not labeled as C sub 2, automatically the solubility is the final concentration. I think I've emphasized it also during the introduction. So in this case, your solubility is based on 290.7. Take note, it's not based on the boiling point of the water and the solid, but rather on the boiling point of pure water only, the concentration that is. So that's 0.539 kilograms of your solute per kilogram of water. So this is our problem, and we are to determine the very important yield. I suggest that whenever you solve problem in any particular topic, in any particular course, it always helps to start with the formula that would lead you to the primary unknown. From that formula, you work your way through to the needed information that or variables that appear in the formula. So we will do that. Let me just by the way, class, this is your asynchronous activity last week. Just read it on any spare time that you have to add to what you already know regarding the use of pure material balances in determining the yield. This is John Copley's way. So you're going to read the example in John Copley's, and this is McCabe's way. So McCabe has a lot of sample problems on crystallization, which uses material balance. Okay, as for this problem of ours, let us go to a Jumpboard that we can use. Okay, let us able to have one. Wait. Let me stop sharing.
Can you say that in the room, please?
Okay, let me share my screen. So in here, we need to start with always the very important given information. So this is our third sample problem already on crystallization. So you can draw your crystallizer here in the form of a box. So what your crystallizer processes is your feed. So this feed is given. I will not anymore go back to the PowerPoint presentation. So I'll just write here the information. So it's 0.56 kilograms per second. And this particular feed has 40% of solids. So this is a 40% aqueous solution of the salt. So in this case, our salt is sodium acetate. So this feed, right, the temperature is at 353 Kelvin. Now, out of this crystallizer, will be producing the crystals and the mother liquor. So I'll place here the liquor, I'll place here the crystals. And this is where we know that our crystal is in the trihydrate form already. So sodium acetate, yes, trihydrate. Now we have, if this is a vacuum crystallizer, there could be some form of water evaporated. So this one is B, labeled as B in our schematic for the crystallizer. It's being mentioned that our B boiling point elevation in our crystallizer is 11.5 Kelvin. Degree Kelvin. Then these are the added information. So the other data given is for the Q. So it's understood to be the heat of crystallization. And this is 144 kilojoule per kilogram of the trihydrate. So you may write the formula here or simply the inward form, the name of the substance. The CP of the solution, referring to the CP of the feed, is 3.5 kilojoule per kilogram Kelvin. Then we're given the lambda, the latent heat of vaporization, and this is 2.46 megajoules per kilogram. Now, if this is not given, this is to be, by the way, based on the operating pressure of the crystallizer. I'll place here the operating pressure of the crystallizer to be 1.33 kilopascal. So this is at 1.33 kilopascal. You're also going to get from the steam table, based on this pressure, the T saturation. So in that case, our T saturation is 290.7 Kelvin. This is also based on the operating pressure of your crystallizer. Okay? And the solubility that is being mentioned, I'll place it here. I cannot place it there, so it will be too crowded. I place it outside. That's the final concentration of your sodium acetate water solution. So you have 539 kilogram per kilogram water. Okay? I think this covers everything, and this is our set information. You are required to determine the yield, the Y. Okay? So we'll proceed to the next page for our solution. So we said we're going to write down the formula that will give us the yield. So what's the formula for the yield in the case of vacuum crystallization based on what is provided by us by Paulson? So I will go to our PowerPoint and share it to you again. Okay. So if you're still on the board, I will not share it anymore. I took the picture, that way I can go straight here without having to go back. Our formula for the yield would be R omega 1, and we have here initial concentration minus final concentration, 1 minus E, and then we have 1 minus C sub 2, and we have R minus 1. So based on this main formula, on the unknown that we're going to determine, we'll check what we need to find. So I think we don't know this yet. We don't also know this one, the initial water concentrate amount. We don't know the initial concentration. We know the final concentration is given. We don't know the amount of water vaporized per unit amount of water based on the available water in the feed, or water vaporized over water in the feed. That's our E. We don't know this, and we know this, and we don't know this one as well. So we'll just label this as our equation 1 and find what we need to find. That way everything here will just be a case of substitution. So if we intend to determine the R first, who can still recall what is the R? It's a ratio of the what? The R is the ratio of the molecular weights of the what? Anybody who can determine, recall? So molecular weight of dehydrated crystals all over the anhydrate. So in our case, our R would be the molecular weight of sodium acetate trihydrate over the molecular weight of sodium acetate only. Can you please find the molecular weights in here? You have your periodic tables with you. Carbon, hydrogen, oxygen, sodium, and 3 times water. Molecular weight is minus 18. So you just check your molecular weight for the sodium acetate trihydrate is 136. And the molecular weight of the anhydrate is 82. 82. And this should give you an R, which is 1.66. So somebody wrote in the chat box. Okay, 1.66, correct. So this is our R here. So we don't have any problem with the R anymore. Okay, now next would be the omega 1 or the W1, the water content of the feed. Sorry for this W. It's referred to as omega 1, but it looks like an italicized small letter W. Your W1 based on the feed. This is your given information. You have 40% aqueous solution of the salt. So somebody wrote in the chat box. Okay. So you have how much is the water content of the feed if it's 40% aqueous solution of salt? That would be what? Omega 1 is correct. That would be then 60% water. So that 60% water, we still need to multiply to the exact amount of the feed. So in this case, I go to that particular slide. Your omega will be your feed, which is, what's the amount of feed? I did not get it. 0.56 times 0.6T. Now this would give you 0.336. So kilogram per second of water present in the feed. 0.56 times 0.6, 0.60. So that would be the water because omega 1 is the water content. So we're done with that. And the next is the concentration. The unit for concentration oftentimes class is the anhydrate over the water or the solvent that is present on it. Okay, if we use this formula, that should be the units that should appear in our concentration. So for C sub 1, based on that, if you have 40% aqueous solution of the salt, how do we write down the C sub 1 or how do we determine the C sub 1? The anhydrate over the solvent. So that would be 0.4 over 0.6, right? You have, this is your solids, this is your water. So in that case, you will have 0.667, okay? Kilogram sodium acetate over kilogram water. You may only write kilogram per kilogram water. That's already understood. That's for your C sub 1 in here. So we know now C sub 1. Okay, C sub 2 is given, so we did not determine it. We determined already R. So the next would be the E. Okay, what's the formula for the E? So I'll go back to our slide and just place it here. Take a picture, that way we won't have to go back there. So your E will now be considering the information, the data that is provided in the problem regarding the Q, the heat of crystallization, and of course the corresponding CP of the solution, referring to the CP of the feed. Okay, so I'll check from the PowerPoint what is our formula for the E. Okay, so since it's quite long, I will just take a picture of that and then share it to you. Okay, so now going back to the board and share this formula to you regarding the E. Water evaporated over water in the feed. So it will have now the Q, the R, and then you have the difference of the initial and final concentration. And this would be added to the CP and the product of the difference in temperature. So this is our formula, times 1 plus C sub 1, which is further to be multiplied to 1 minus C sub 2 R minus 1. So this would be our numerator. And you will have here lambda, latent heat of evaporation. And then we have 1 minus C2. And you have here R minus 1. It's the same thing that you are seeing here. And then we multiply this with, subtract rather from this the product of Q, R, and C sub 2. Okay, now your T sub 1 here will be the temperature of the feed, and your T sub 2 will be the temperature of your solution inside the crystallizer. So with everything in here given except known already, except for this temperature, then we just simply use the BPE that is given in the problem. Now I'll place it here. Your T sub 2 is equal to the T saturation plus the boiling point elevation. So the T saturation given already in the problem is 290.7. So this is 290.7 plus the BPE. The BPE is 11.5. So you have now your T sub 2 equal to 90.7 plus 11.5. So that would be 302.2 Kelvin. So this is our T sub 2. Now I think everything here is known except for the E that we're going to find out. So we'll substitute values. Your Q, 144. And then the R, 1.66. Your C sub 2, 0.539. And your, oh sorry, this is C sub 2 by the way that I took. Okay, so I need to place C sub 1 first. So we determine C sub 1 somewhere here. 0.667. So 667. And your C sub 2 is 0.539. Okay, plus, so your CP, remember your Q is already in kilojoules, so you make sure that your CP will also be in kilojoule. So this is 3.5, so your units will agree. So this is 3.5, we multiply to T1. The T1 is the temperature of the feed class, which is 353. Because this talks of the difference in temperature. So 353 minus 302.2. plus, okay, I will write it here on top because it will not fit in anymore. I'll place here, okay, break class. Hindi siya mag-igo da gyapon. I write it here below, ha? You just continue here below. And the denominator, I'll just write a little bit further below. So you will have 1 here plus C sub 1, which is 0.667. And you have 1 minus 0.539 for the final concentration, multiplied to the R, which is 1.66 minus 1. Okay? This is still part of your numerator. The denominator, this one, I'll place a line here so you would know that it's part of the numerator. I'll place the denominator here. So your denominator, so you would know this is still E. So you have the numerator as written in the previous page. Our denominator will need the lambda. So it should be in kilojoules as well. Now this one is in megajoules, so we'll convert it to kilo. That way, the kilojoule unit will just cancel. The one in the numerator and in the denominator. So I forgot. So this is 2.46. So that would be, in this case, at least here, 2.46 times 10 raised to 3 to make it also kilojoule. That's for the lambda. I need the 1 minus C sub 2 again. So I will have here 1 minus 0.539 for the C sub 2. The R is 1.66 minus 1. Okay, I have this. And then minus Q. I'll close this one. Minus the heat of crystallization. Here's the Q. I had it here already. 144. Okay, 144. That's based on this formula. The R is 1.66. And what else do we have here? C sub 2. 1.66 and the 0.539 for the C sub 2. So the value that you will have here in the numerator is this particular expression you're seeing here in the previous page. The denominator is the one that you are seeing here. So your amount of water evaporated from the initial feed, let me check. You double check, please double check. Your numerator is 221.55. Your denominator is 1156.04. Let me check. So this will give you which is, okay, I think this one is, let me check. Okay, so this is 1 4 rather class 1456.04, and you will get here a 0.152 kilogram water evaporated per kilogram water in the feed. Okay, that would be the E. This E, you need to substitute in here, in our equation 1 together with the things that we have determined here. Okay, so your Y is equal to, so this is from 1. Okay, R omega 1. I need the omega 1.336. So I have here 1.66, 0.336, and we have here concentrations. Initial concentration is 0.667 minus 0.539. Okay, memorize it already, 539. Then I have 1 minus E. So 1 minus 0.152 here. And the denominator will be 1 minus C sub 2R minus 1. 1 minus 0.539, 1.66 minus 1. Let me check if I got it right. Okay, 1.66 minus 1. Okay, so you will have now the yield crystals with the unit kilogram crystals of sodium acetate trihydrate. Let me check if it will be same as the one that I have in my old notes.
Number 6, E.G. snipped behind the tree where a people was tied to. For number 6, you have to circle it because it happened in the story. Number 7, the corn dwellers ran away when they saw E.G. Yes, no. No. Very good. Number 8, a people blinded the corn with a sword.
Okay, my answer is 0.1817 kilogram of your sodium acetate trihydrate. Okay, this is your yield. We wrote in the chat box 0.18. Okay, that's correct, Aina. So 0.1817. So this is our yield for problem number 3. Given the information regarding BPE, heat of crystallization, and latent heat of evaporation in here, based on the operating pressure of the crystallizer. So any question here before we proceed? Okay, so none. Okay, so I will now go back to our slide. Okay, and then proceed to the part after sample problem number 3. Okay, so in here, we're ready with the different steps in the crystallization process after knowing how to use material balance and the concept of heat transfer using the boiling point elevation whenever solutions have solids present on them already. Now, so when we speak of nucleation, it's the crystal creation from a supersaturated solution. So this creation of crystal happens in a supersaturated solution. Now, when you speak of crystal growth, it's the increase of the crystal size up to the desired size by growth from supersaturated solution. So again, growth will only happen in supersaturated condition. Now, what about dissolution? The dissolution is when your solid returns back into solution, meaning after it precipitated out as a solid in your solution, it went back into solution. So that's dissolution. And this happens when we're in our solution attain what we call a non-saturated condition. Okay. Now, there are two things that happens during the process of crystallization. The first one that I'd like to discuss here is the Ostwald ripening. This is the slow aging or the size evolution, principally an increase in the size of your crystal with time of a crystal population in the vicinity of the saturation. So at saturation condition, actually, class, there is already a start in the growth of these particular crystals. Although the growth is enhanced when we have a condition which is super saturation. This ripening is a condition that is attributed to Mr. Ostwald. So the slow aging or size evolution, increase in size of your crystal is the Ostwald ripening. Now, agglomeration, actually, it's being discussed here in contrast with another term, and that would be in the next slide. So, agglomeration is the formation of crystal clusters linked by crystalline bridges. And in this case, when you have already agglomeration in which you have the formation of crystalline bridges, your crystals are said to be stable and will never come into a point of dissolution, meaning it dissolves back into solution due to this particular formation of the crystalline bridges. This happens in a condition known as agglomeration. Now, it will be contrasted with a different term later on, and we will for now discuss the different steps that happens in the crystallization process. Now, in crystal growth, in crystallization, growth plays an essential influence in the crystal size and shape. So the way we grow or the way we let the nucleated crystals evolve its size has something to do with the shape and as well as with the size of the crystals that will be formed later on. So the growth of a crystal phase results from the progressive. So it's a progressive integration of atoms or ions into the crystal lattice. So a little portion now grows into a bigger crystal by means of this integration of atoms or ions in the lattice. Now, the growth kinetic process is divided in several consecutive steps. So, pasunod din siya dapat. So, the growth rate is determined in these particular steps and in any production steps and in any progressive steps of whatever it is that we are making or manufacturing, everything is determined by that slowest step or by that slowest part in the procedure. The rate of the entirety of the production of whatever it is dependent on that particular step, which is the slowest. Okay, now we proceed. So let's represent the crystal surface in here. So if it's likened to a stair, so everybody I'm sure is familiar with the stair, we call this part in here as the terrace. Okay, ang latakan. And we call this particular atom or ion that needs to attach itself to this particular crystal surface as the adsorbed species. It gets absorbed. And if this is the terrace, we refer to this one as the step. This part in here. Okay, this is our step. The one in the corner is the very crucial part, which is what we call as the kink. And these adsorbed species get to attach themselves in this kink. So if this one gets attached in here, this other one will get attached itself again until this particular step is completed. Then a new species gets absorbed in here until we have one finished terrace in here. So they are now in label with this step in here, with this upper step in here. Okay. Now, there are different adsorption sites for these atoms or ions into our crystal lattice. So we have the terrace, this one. In here, we only have one bond. It's only a single bond, so meaning it's not as stable as the others. In the step, in this side in here, we have two bonds. This space here and this space in here gets bonded. The most stable is the kink, wherein we have this bond in this side, this bond in this side, and the one at the bottom. So that's your kink. Wala, next slide sa akon, miss. Wait. Does everybody see the slide? Same here, miss. Hala, wait, class out. Wait.
The different steps lang.
Where are you now? The different steps of the crystallization process. And what do you see in that page?
Nucleation as sa agglomeration, miss.
Oh, okay. I'll go back to the main slide ha, and then escape. Then project the entire thing na lang. How come you don't see? Yes, ha? Where is it? Here. Let me share na lang the unprojected slide. Okay? Sometimes, nag-bisyo. I don't know why. Hindi ko ka-intindi nga. Do you see the entire slide now? The green one. Ang green man gali ang puno, no? With the stair-like thing already.
Yes, miss.
Kasi hindi ko na pag-i-project para makita niyo ang below. So where was I now? If this is your crystal surface, we refer to this as the terrace. We refer to this as the step. This is the step. Ini nga side, kag ini nga side amo ng step. Doon nagka-L na siya bilang. And we refer to this as the kink. We have this face, and the bottom part. Now, the most stable bond site for your adsorbed species out of these three is the kink part, because in here you will have three bonds. This part here in front, and the part at the bottom. The step will have only two bonds. So you have this part and the part below. If you have on the terrace alone, if the adsorbed species will not attach itself to the kink, it's only a single bond. So whenever the bond is not so stable, there is a tendency for your adsorbed species to not be formed as part of the crystal lattice that is going to grow bigger and bigger in the process of crystal growth, as stated in here. So it's important that this adsorbed species gets to attach itself on the kink. Okay? Now, I will go to the next. Now, the different steps that is being mentioned here, so this is more general on what happens, is in here. It's illustrated in here. So number one, the transport. So the bulk diffusion of the solute ions or molecules towards the crystal face. So they get to be transported via bulk diffusion in here, in your crystal lattice. The second is the adsorption. Adsorption on the crystal surface, which is a potential growth units. Now, it could be bidiffusional diffusion of the growth units on a terrace or the terrace. Adsorption, so next is adsorption of the growth unit to a step. So as these adsorbed species get to attach themselves on the kink, makompleto na siya sa dire. And then it gets to shall I say, fully form this what we call step. Then in the fifth, you have the unidiffusional or unidimensional rather diffusion along the step. So kung diriya class, uni lang siya. Just like what is being described in here. Kung ara ka lang sa terrace, single band ka lang. So amo na unidimensional siya. Unidimensional ang imo nga diffusion. Adsorption of the growth unit onto a kink is the integration or the most stable part in the formation of the crystal lattice. So ang pinaka-nami nga adsorption site, as I have mentioned a while ago, is your kink, because this is when your adsorbed species gets really integrated into the crystal lattice. So if you're going to summarize the different steps in the growth mechanism, because the last part in here refers to whether it's bidimensional or unidimensional, it would be summarized in three steps. The transport, the adsorption into potential growth units, and later on, the adsorption into a more stable adsorption site in the case of your kink of your adsorbed species. So transport and adsorption. It could be bidimensional or unidimensional. That is for your crystal growth. Okay? Now we go to the consequence of what these steps here is going to make. At the end, ano gid ang resulta? Sine. So you have the progressive filling of the step by growth units, progression of the step on the surface, formation of the crystal lattice layer by layer. So the formation of the crystal lattice, the formation of the, or rather the growth of the crystal will be, in this case, layer by layer. Now, I mentioned a while ago about agglomeration, and it's being contrasted with just simple case of aggregation. I think this one you could see now, okay? The case of aggregation and agglomeration. So aggregation is also the formation of clusters of crystals, but the forces that links these crystals are weak, and they are van der Waals forces. Whereas agglomeration happens when there is collision, then afterwards aggregation. So this aggregation is just part of this agglomeration. So they collide and then they aggregate, and then they form these particular crystals which are connected or linked together by crystalline bridges. These crystalline bridges are, shall I say, formed during or in the formation of a supersaturated solution already. And your solution in this case, or your crystals, will not anymore go back to the solution in the case of dissolution, because you have already the formation of the crystalline bridges. So if you would be asked to distinguish aggregation from agglomeration, your aggregation is just part of the process of agglomeration. Okay, this is aggregate, this is agglomerate. So by the illustration, you could see that in here you are forming a more solid, stable structure compared to this one. Now we go to the types of crystallizers, just to make use of the time. So we have the first part here as the cooling crystallizers. And the most common ones are the non-agitated vessels. There is no form of stirrer or agitation in this particular vessels, and this is of course the simplest. The simplest of type of cooling crystallizer wherein it is an unstirred tank in which a hot feedstock solution is charged to an open vessel and allowed to cool, often for several days, by natural convection. Natural convection, not enhanced degree of cooling, no stirring that happens. Na-stack up naman siya. Escape ko na lang. Show ko na lang bilog. Hindi na ko class mag-project. Dadakoon ko na lang para magdako sa inyo. Okay, I'm now on types of crystallizers. You can see? You can see already?
Yes, ma'am.
Okay. So what happens here? Paano na miss yati dugay-dugay na karon kay wala man siya stirrer, you just simply dispense it in a particular receiver and then let natural convection pull it down. So what happens here is there is this what we call metallic rods that can be suspended in the container itself so that large crystals can grow on them, thereby reducing the amount of product that sinks to the bottom of the unit. So the nucleation process in here is enhanced through this particular metallic rods that may be suspended in solution. So the thing is, if there are solids already forming in your solution in the process of cooling, which will take days in this case, the solids will get to adhere on these metallic rods and they will not sink at the bottom of the container. However, this is really very, shall I say, labor intensive because the product is usually, in this case, removed manually. And at times, it needs the products to be scraped off from these suspended metallic rods. This is in the case of cooling crystallizers, which is the simplest, nga non-agitated siya. We can also have a case of, see, this is still, by the way, class, a continuation of the non-agitated vessel. So because cooling here is low, large interlocked crystals are produced which retain mother liquor. And thus the dried crystals are impure. What happens in here, if you're going to liken this to the formation of the sugar crystals, if you're going to spin off later the solids that are being formed out of your from your crystallizer, place it on a centrifuge. That way it gets separated from the mother liquor class. There will be a lot of molasses that will be formed. your crystals are very impure. The greater amount of molasses that is being extracted in the process of centrifuging these particular solids, separating the crystals from the liquor, of course means that your process is not really that efficient because your crystal purity here is affected already. So your dried crystals are very impure. Because of the uncontrolled nature, you do nothing. There's no stirrer. You simply let natural thing there, let the crystallization occur. Product crystals are ranged from fine dust to large aggregates. So ang buwa, the common sense man, iban pino, iban gabigol-bigol. So hindi sila uniform ang size niya. So labor costs are high, as mentioned, but the method is economical only for small batches. Since in here, it's of course, it's simple since capital, operating, and maintenance costs are low. Maintenance costs are low because there are no moving equipments to regularly maintain and check. Although in terms of productivity, purity, and quantity, it's low and space requirement is really very high. It's very, very common sense when you say space requirements is very high. Why? It's because you have to let it stay there for how long, and then you need a lot of space for your solution to really cool down. And if you are, this is not really for large batches because if you have large production, then you will really need very big space for this one. Okay, although in terms of capital cost, gamay siya, kahit wala manggig kamayo i-design. Now, what about the agitated ones? So this time we'll have some form of agitation already. So installation here of an agitator is added to an open tank crystallizer, which gives small and more uniform crystals. And of course, will reduce cooling time, translated to batch times. Because less liquor is retained by the crystals after filtration and more efficient washing is possible, the final product has higher purity. So this is just comparing the non-agitated product with the agitated products. So water jackets in this case can be further installed. So water jackets are usually preferred to coils for cooling because the latter, referring to the water jackets, often become encrusted under the coils. The latter, the coils, often become encrusted with crystals and the inner surfaces of the crystallizer should be smooth and flat to minimize. So if you're going to use coil splash, just like with the suspended metal rods, dira na sa matapik ang solids, dira na sila mag-grow. So and at the end, if it gets encrusted with crystals, there's a need to clean these coils. That way, your heat transfer, in that case, the process of cooling would still be maintained. If not, a more degree of heat transfer will be reduced because of the presence of these solids that attach themselves one over the other in your cooling, shall I say, in your coils, cooling coils. Now, operating costs for agitated coolers are higher than simple tanks. And although the productivity is high, product handling costs are still high. So these are, I think, the first crystallizers that were designed then. The agitated vessel as taken from our textbook may look like as simple as this one. So this is our agitated cooling crystallizer.